We are back once again. This is day 40 of LeetCode every day. I actually was doing problems earlier, but I forgot to hit the button. So we actually already fried quite a few problems. We did all nodes distance k in a binary tree, which was pretty cool because you could visualize the tree that we're trying to find, the node distance k for as a graph, and then you can do a level order traversal on the nearby nodes, which is pretty cool. We also just did kth smallest element in a VST along with majority element, and now we're on lowest common ancestor, which I started and then I was like, wait a second, we're not recording. We haven't been. This is majority element. So lots of things happening. Reflections. Going to try doing 1 hour 30 sessions. This is to 90-minute sessions, which is what we're already doing, but with a break around 20 minutes, so you can do sprints. But yeah, this would be like our second session today. There's still one more session to be done, but yeah, you know, the goal as always, we're trying to finish the grind 75. Then if we finish all that, right, there's actually a total like 150 problems in here, which is pretty dope. If we could finish all of these problems, and in addition, right, we're actually doing a lot of tree problems right now, just because I really want to grok the tree angle on problems. So there's also a lot of problems we did today. We did right side view tree, which was actually a really good problem. Another way to use level order traversal. And then maximum depth, which is pretty straightforward actually, but really getting the hang of these tree problems. And then maybe we'll do, not really sure where to go from here. I mean, we only have, so we're actually 41 of 75. So we're actually making good progress. It's about 34 problems remaining. That would be pretty dope if we could finish all of those. That being said, yeah, if you're doing something similar, let me know. If you're not, why not? Why not do some problems, right? Yeah, but don't forget to join the Hyperbolic Coding Chamber Discord. Thousands upon thousands of people are joining every day. We're actually talking with Discord. We actually got a 6th server open, so we actually got a little bit more space, but it's gonna get filled again soon. And yeah, I mean, more grinding to be done. I'm actually going to record this as a shorter session, just because I also do revision, but I don't know if revision is that interesting to watch. Maybe nor is this. I think the thing that we're trying to get at is just having a history or proof of work done, which I think is pretty cool. So yeah, that is the goal. Still recovering from the sickness, the final sickness, and I think we should be all done by Monday or Tuesday. That being said, there's more to get done. So I'm just going to jump back into the original problem, whose lowest common ancestor, binary tree. So given a binary tree, find the lowest common ancestor of 2 given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between 2 nodes. P and Q is the lowest node in T. It's both P and Q as descendants. Or we allow a node to be a descendant of itself. So we have the root tree here. We have P and Q. We want to find the lowest node such that P and Q are descendants of it. That would be 3, since 5 and 1 exist here. I think a requirement for this problem is that each node value is unique. For this one, we have P equals 5 and Q equals 4. The lowest node that has both P and Q as descendants, or is P or Q itself, is 5, because 5 is node 5, and its descendant is also 4. So actually, the way that I'm thinking about this now, maybe just to generate some ideas, is we could have P and Q will exist in the tree and P will never equals Q. That's actually a really good point. All node values are unique. Let me just generate a few potential solution paths. What if we did a level order traversal? If we did a level order traversal, we'd have 3, 5, 1, 6, 2, 0, 8, 7, 4. And if that was the case, right, we'd have access to these particular nodes in level order traversal. And from there, it's important because what we want is the deepest node. So we could additionally do, so we'll do at level order traversal. I mean, just as a potential solution, level order traversal with a array, right? And if we find during this level order traversal a particular node that has both P and Q as its subchildren, or it is P or Q itself, right, then we'll push on to the array. At the end, we should be able to return last index in the array, right? So we could generate a few answers for this. The first one would be 3, right, where 3 has 5 and 4 as descendants, right? Additionally, 5 is 5 itself, and I mean 3 has 5 and 1 as descendants. That's the only answer possible. But let's say they wanted 4 and 2, right? 3 could be an answer, 5 could be an answer, and 2, which would actually be the best answer, which would be the last index in the array if we go by level order traversal. So do level order traversal. And so the way that we'll actually be able to check if these two values exist is by doing, we'll have a depth in exists function, which would be done as a depth first search. Just to prototype how that could work, let's say we call it on node 5, right? We want to say, hey, do you have P and Q? We could say, okay, you have P or Q as a descendant, right? And we could say, okay, well, 5 is where we start, and we'll do just an in-order traversal. We'll do 5, 6, 2, right? 7, 4. I mean 5, right? Go left. Nope. We're looking for 1 or 3. Let's do this example instead. 5, are we looking for 5 or 4? Go through 6. We go through 2. We check 7. Before we do return here, right, we do find that it does indeed have it. Right, so it does indeed have it. Right, and at the same time, we can check if the node itself equals P or Q. Right, so this exists function is going to have to do a little bit, and it's going to be called twice during the level order traversal. So to start the level order traversal, we'll start with root inside the array, and we'll say while Q length does not equal 0, and we'll say if, we have to make sure that we pull a node off of the queue from the front. This node is going to be equal to cur. Most importantly, we want to make sure that this current value exists. And if this current value exists, then we want to check some things, right? The first thing we'd like to check, right, is if cur.val equals p.val, right? So if cur.val equals p.val, right? If cur.val equals p.val, right, that would mean that the node itself is p. So if the node itself is p, right, and to exists, right, given a node cur, does the value q exists, right, and that we know that we would have in a node that we are interested in, right, which would be cur, right? Cur is a node that we are interested in. And so it would actually be if we also have another case, right, which would be very similar to our first case. If cur dot val equals q dot val, and if cur and what actually exists is not q dot val but p dot val, right, then this is actually a node that we're interested in. This would actually be a node that we're interested in. So in that sense, we could return cur as the tree node. Right. Now, if it doesn't, right, then what we'd like to do is just push. We don't want to return cur, that's my mistake. We said we want to have an array of answers, right? And what we would do is we would do cur dot push answers. We do answers dot push cur. Then we'd want to push if its left and right nodes exist, right? We want to push its children on to continue the level order traversal, right? So we'll say if cur dot left, right? Then we'll do q dot push cur dot left. We'll say if cur dot right, say q dot push cur dot right. And so what we could return at the end is answers, so answers dot length -1. And what we're going to need is to finish this is this exists function, which would take a node, which would be a tree node or null, and a value that we're searching for, which is going to be a number. Return a Boolean, right? So we want to know if this value exists, right? So let's just say we're at 5, right? We don't have to check if it might be easier actually if we check if it doesn't exist, and then we can not it. So what if we said doesn't exist? Would that be easier? We could say if the current node. Well, how do we know if it doesn't exist? We only know if it visits the whole thing. So actually we could do exist, and instead of anding these Boolean logical expressions, what we'll do is OR them. So if the node exists, we're going to check some things. Otherwise, if it doesn't, we're going to return false. But what will make sense of it is if we do if node.val equals value, then we're going to return true, right? Otherwise, if it doesn't, what we're going to return is actually it's better if we do it this way. We'll return node.val equals value, or exist of node.left, right, value, or exist of node.right value. And so given 5, right, if we're given 5 and we're looking for 1, let's say we're given 5, we're looking for 4. We're going to say, okay, 5 exists. Does 5 equal 4? No. Let's check the left subtree. Does 6 exist? No. So now we're going to check if it exists. So does 5 equals 4? No. So we're going to do or exist of node.left. So we go to 6. 6 equal 4? No. So we do exist of left. Right doesn't exist, we return false. We return false for right subtree. Now we're going to 2. Right, does 2 equal 4? No. Right? So we're going to do left and right. So left subtree, does 7 equal 4? No. And does right equal 4? Yes, we finally return true. And one of these ORs should give us the answer that we were looking for. We just need to do an S. We named everything exist. So it looks like we got all those references to date. So we actually return null. So we're checking these special cases only. We actually want one final case, or right, we call exists, right, for cur with q.val, right, and exists for cur with key dot val. Right, so if one of them can be used as the node and exists, right, or if the node itself can't be used as a node and it just exists as part of the subtree, right, then we would be in business as well. Ooh, this is actually quite a slow algorithm. So this is actually quite slow. So we're actually doing a lot of checks of exists. So we could actually simplify this with q exists per q.val to speed it up just a little bit. All right, wouldn't that is that q exists, but q exists as a subchild, or q subchild, or actually I guess we can call it q exists and p exists. That way we don't have so many wasted calls. We'd have q exists and p exists, as well as q exists and p exists. See if this is a bit faster. So this is actually the same exact speed. Actually, it's even slower. So the time complexity of this would actually be, for each node, we're checking the value exists. So we could speed it up just a little bit by having the exist function return a map that we can check if p exists. Another way we could speed this up is if we created a how could we speed this up? How could we speed this up? We could use a map. What if we iterated through the entire binary tree and created a map. Then we could look through it twice. So it'd be linear time with two calls. And then there we could check if the value exists. As a subtree, we set up to a level order traversal. We could say 5, and we'd have a list of all the numbers in 5. If we did this with a depth first search, we could build this tree up so if we went bottom up, we could build the tree, this map of values up. So this map would look something like, for 2, we'd have 7, 4, and this could be optimized even further with this number mapping to a set. For constant lookup time, and then 5 would look something like 2, 7, 4, and 6. That would be faster. So what we're doing right now, exists of node.left or value maybe we can use level order traversal to our advantage instead. If we're doing level order traversal, doing level order traversal, maybe we can maybe we can speed it up, since if we're going downwards through the tree, and let's just say we're looking for the nodes such that P and Q are sub children or descendants of that node. Be at 3, and we'd say, have we seen 5? We have, and have we seen 1? The problem is a little hard to know exactly what node. Let's try for this example. We have node 3. We're looking for 5 and 4. We have 5, which is impossible to know. Or if we do the level order traversal, we could have a running lowest node. We'll say, well, if we're looking for 5 and 4, we'll check 5. Have we seen 5 yet? Yes. We haven't seen 4 yet. We can say that we've seen 5, so we have a boolean, seen P. Then we'll do 6, do 1, 0. So maybe we'll start with root being the lowest node. Let's say, have we seen 5? We have. Have we seen 4 yet? We haven't. Then we'll say, okay, 6, 2, 0, 8, then we'll say 7, 4, we'll say we have seen 4, If we want the lowest node such that we can, is a descendant, lowest node such that P and Q are descendants of the node. what if we just find P and Q, 4 and 1, and we had it visit all its neighbors to find the change it to here to 3. What if we use some kind of graph to say we find 4 one of the nodes are looking for first, like P, and we could use a graph traversal algorithm to search our neighbors, which would be our children plus our parent. We look upwards to 2, right? Look at the neighbors. We already visited 4, right? We could check 7, right? Do a level order traversal, 7 and 5. No children for 7, 6, right? But 5 is actually looking for, so the closest node as us both would be 4 and 5. Oh no, here we're looking for 5 and 1. So our level order traverse would be 6, 2, 3 with our neighbors, and we could find 1. The node that connects them would be 3. In this case, the node that connects them is 5 itself. So the graph kind of breaks the downward angle of the goal, which is the lowest common ancestor, or the direction. So we visualize the graph probably isn't a good idea. Just speed it up. This is a binary tree, so we have no guarantee that the node we're looking for can be in any specific section of the tree. I think the only way to speed it up is by using space. So if we were to look through the entire tree once, and we knew all the children of every node, and what we could do is just through 5, and so we did level order traversal on both the left subtree and the right subtree. Actually, maybe not. How could we speed it up? Oh, I think I see. So we actually visit the whole tree because we never really know what the lowest common ancestor is. So we just keep going all the way until the end. That could be why it takes so long. So you have to visit the whole, maybe you don't have to visit the whole tree to know the lowest common ancestor. So if we have a potential answer here, answers.push cur, potential answer here, 3, we have 5 and 4. 3 is a potential answer here. It's level order, so we end up visiting the whole thing. Curd and exists checks the entire subtree. We could speed this up maybe by not actually bound equals value, and then it does another 2 more calls. That's probably why it's taking so long. Let's see. First, given nodes P and Q are to be searched in a binary tree and then their lowest common ancestors to be found. And resort to a normal tree traversal to search for the two nodes. Once we reach the desired nodes P and Q, we can backtrack and find the lowest common ancestor. I see. Looks pretty intuitive. Find 9 and 11. Traverse the tree in a depth-first manner. The moment you encounter either the nodes P or Q, return some Boolean flag. Flag helps you determine if we found the required nodes in any of the paths. Least common ancestor would then be the node for which both the subtree recursions return a true flag. It can also be a node which itself is one of P or Q, and for which one of the subtree recursion returns a true flag. Talking about our if statement here. So this version is linear time. Ah, 2, 4, 8 backtrack. Oh, no. 2 is know where we have left equals true. That is true. You could just go through and just say, hey, left node tree, or am I it? Or is it the right node tree, or am I it? Linear time. So there's a linear time solution with recursion that we have to solve next time.